Hi, I'm Aaron. We're going to be talking about rotating assemblies in this show. What is the rotating assembly? That's basically everything inside the motor that rotates. The crank, the rods, pistons, rings, bearings, harmonic balancer, flywheel, all the stuff that's involved in that. You know, a lot of people can build an engine, and it's really not about whether you can build an engine or not build an engine. The trick is knowing which components to choose for the right job. For instance, we're not going to use a stock crank or rods on something like this that's blown, a 700 horsepower motor. And you're not going to take a stock motor and put a billet crankshaft in it or titanium rods or something and put $10,000 into something that makes 200 horsepower. It's just way overkill. So it's not all about price, power, or anything like that. It's about choosing the right components for the specific job that you're doing. You know, I get a lot of calls. People call up, hey Aaron, how much is it for like a 500 horsepower motor? That's really not the question you want to ask. The question you want to ask is, how much is it for a 500 horsepower motor that will withstand its own power? And what I mean by that is, you know, making power is a no-brainer. It's really easy. The problem is, you can make all kinds of power, but the components that's inside the motor might not withstand the power it's making. So, I mean, for instance, I can make 500 horsepower with stock pistons. Mind you, they're domed pistons. It'd be like a 13 or 14 to 1 piston. But we could do it on a stock rod, and the pistons can be cast. We could use stock cast rings, stock bearings, even a stock crank. And guess how long it's going to last? Well, about 11 seconds, and it's going to come apart. So you really need the components that's going to withstand the 500 horsepower, or it's just going to fail on you, and all the money you spend on it is just down the tubes. Let me give you a scenario on this. Let's take like an 800 horsepower NASCAR motor. You're talking a $40,000+ motor. Why is it $40,000+? Well, because of the crank that's in it, the rods, the pistons, basically everything in the rotating assembly. And mind you, the heads are expensive and stuff too, but a lot of the money's in the rotating assembly. Let's take like an 800 horsepower drag motor. That's not a $40,000 motor. It's about probably a $15,000 to $20,000 motor. That's substantially less. Why? Because it's only got to live for 7 or 8 seconds at a time down the quarter mile. It's just getting short bursts of power. It's not like a NASCAR sitting on a track going 9,500 RPM for 3 or 4 hours at a time with millions of dollars of contingency money behind it. It really has to last and withstand. So the price really has nothing to do with the horsepower. It had everything to do with the quality and strength that's in that motor so it can withstand all the rigors and the forces and loads that are on that thing and the RPM and just stresses that are on that, so it just keeps going. So let's elaborate a little bit on that about strength, quality, and price with some basic tools, because we've all got tools in our toolboxes. Well, look at this typical Phillips screwdriver. This right here is just your cheap 99-cent screwdriver. And of course, if you look at the tip, it's completely worn out. I mean, it lasted 3 or 4 screws going into some wood, and it was over with. If we look at a good quality screwdriver, now this one costs a few dollars, but it's lasted years and years and years, okay, and it's the next strength up. But the tip is not worn out. I've been using this thing over and over and over. Now let's equate this to crankshafts or rods or pistons. Now the 99-cent screwdriver is like your stock equipment. It's okay, but if you start really torquing on it or anything like that, you just blow the tip off. So you need to go to the next one up. Well, the next one up is a good quality, but guess what? This screwdriver costs a little bit more money, but it lasts a lot longer because it's stronger. Now, just so you know, we can go to a really high quality screwdriver. This is one off one of the tool trucks that comes by the shops. And I've had this one for, probably 15 years, and I've used it for everything that you can imagine. I mean, even stuff you're not supposed to use it for, hitting it with a hammer and putting vice grips on it and torquing on it. And guess what? The tip is still just like the day it was when I purchased it. Now, the difference with this is, this screwdriver right here costs more than this whole set right here. Okay? This whole set was just a couple of dollars. So what's it worth to you? Is it worth using a stock equipment and putting a lot of torque to it and having it fail? Well, that's like having stock components in your engine, putting a lot of horsepower to it, like nitrous oxide or a blower, or just expecting it to wind up and make a lot of power. Guess what's going to happen? Just like this tip, it's going to fail because it's not strong enough to withstand the power that you're putting or the vigors and abuse that you're putting it through. So you upgrade. Well, you upgrade to something like this, which is equivalent to like an aftermarket crankshaft or aftermarket rods or aftermarket pistons, better, stronger pistons. Of course, it costs more. Okay, but it's going to withstand better. Then, of course, we go into the high dollar stuff. This thing will take everything you can throw at it and then some, just like billet crankshafts or H-beam rods, 4340 rods and stuff, and super light forged pistons. They're expensive, so is something like this, but you get what you pay for. Let's put this in even more perspective. Let's take a monster motor like this and say the head bolt. You're talking about a bolt that's going to take 65, 70 foot-pounds of torque on average, sometimes even a little more. Well, if we're going to choose the tool to do that, we're certainly not going to pick like a 1/4-inch ratchet like this. You just blow the head apart or just bust the socket wide open. Okay, so we have to choose the right tool for the right job. So if we go up to the next one, this is also a good quality wrench, okay? A 3/8 drive and about 60 or 70 foot-pounds of torque. That's about the max on this thing before the head starts to break. So this isn't really a good tool for that particular job either, but it will take it for a few times. So let's put this into more perspective for you to understand that. Let's say someone calls and says, hey Aaron, I want you to build me a 450 horsepower motor and I got $2,500 to spend. It's not very much to put into good quality components to withstand that kind of power. Making it make 450 horsepower is no big deal. I can do that. You put a nitro system on it and on a stock motor and it'll make 450 horse. The problem is it won't be able to withstand that kind of horsepower for very long. It's like this ratchet trying to torque it to 65 or 70 foot-pounds all the time. Man, you're asking for this thing to break. You need to go to a stronger unit like that to take that kind of torque. So the same thing, we're going to jump up to something that'll take that kind of torque, a 1/2-inch drive. This thing will take 65, 70 foot-pounds all day. So on something like in a motor, yeah, 450 horsepower, you need components in it that will withstand that kind of power time and time and time again. Thing is though, the larger, heavier duty wrenches like this cost a little bit more money. In retrospect, we're not going to take something like this and come over here and try and take off a little teeny carburetor bolt, or we're going to snap the bolt off. Not that a crankshaft, a good strong crank, is going to hurt anything inside the motor, but you don't need to spend $1,500 or $2,000 on a wild crankshaft inside of a motor that's going to make 450 horsepower. You don't need to overkill. The trick is spending the right amount of money, getting the right amount of quality, and letting your components to do the job that the engine's designed to do. Surprisingly enough, there's really nothing in the rotating assembly that has a whole lot to do with making horsepower. I know a lot of you are probably going, oh no, no way. Seriously. The only thing in the rotating assembly that has a lot to do with making horsepower obviously is compression and stroke. And little factors like ring friction or piston friction, stuff like that. But really, most of the horsepower comes from the cam and the heads and a given amount of compression. You really buy quality and strength, and most of the money that goes into motor is in the rotating assembly, and you're paying for the quality and strength. But it really doesn't have a whole lot to do with power. So when you're choosing components, don't look at the price for how much power you're getting. Look at the price for what kind of quality and strength you're getting and how long it will last through the abuse and vigors that you're going to put it through. All right, now we're going to talk about crankshafts. Now there's many different styles and types of crankshafts for many different uses out there. Now most vehicles out there have cast iron crankshafts. And this one right here is a typical cast iron crankshaft. And you're talking about 98% of the vehicles out there have cast iron crankshafts in them. And they're plenty strong for most stock, even performance usage. Now the next one up from that is still cast iron, but it's a nodular iron. It's just a little different alloy. It's a little bit stronger. Now the next step from that is very popular crankshaft is a cast steel crank. This is a SCAT 9000 series cast steel. They're about 15% stronger or so than a cast iron crankshaft from the factory. It's a good choice for your basic performance use. Now the next step up from that, of course, is a forged crankshaft. And there's lots of different forging alloys out there. Most of them are either 4130 steel, 4340 steel. There's even one that's called EN30B, which is just a really high-end steel, also very expensive. And even beyond that, they go into billet, and I'll show you a billet crank next. Well, we'll talk about forged cranks. Now, some cars, factory performance cars, some of the Corvettes, cars like that, came with forged cranks right from the factory. And they're different alloys. And a way you can tell a forged crank is by the parting line. If you look up at the parting line, what I mean by that is when they actually stamp the crank out of a solid bar of steel, they'll stamp it out and forge it. It's hammer forged. So you look in the front up here, and there's a parting line. It's really wide. Okay, that means it's a forged crank. Now if we look at a stock cast iron crank, they have a very narrow parting line because they come out of a mold. And if you look at this one, it's an extremely narrow parting line. And that's basically where the two halves of the mold came together, and then they poured the molten steel in. It just fills the mold up and out pops the crankshaft. Where when a forged crank is, they put a solid bar in there and they hammer the heck out of the thing, and it actually forms a crankshaft. And the reason they do that is for the granular structure. When you have a cast iron crank, the grain in there, just kind of in the metal, just kind of goes every which way it wants to go. When you forge a crankshaft, the grain is more in line and it makes the crank much stronger. So let's talk about the grain in the crank and what that means. Basically, that's the molecules of the steel in the crank and how tightly bound they are, and also the direction. Grain does have direction. So first off, we're going to talk about the granules of the grain. If we look at styrofoam, this is a pretty good analogy here. Styrofoam, if you look at this one here, the little styrofoam balls that are compressed together are much smaller. So this piece of styrofoam is actually much stronger. If we look at this one, the little grains inside are actually much larger. They're spread apart more, and this one's not quite as strong. It's kind of the same way with cranks. If it's a tighter granular structure, it's obviously a stronger crankshaft. When you forge something, you're actually compressing all the grain together and lining it up in a specific way, which makes it much stronger. And let me equate this to something a lot of you can understand. Let's take a piece of wood. All right, here's your typical piece of wood. Now consider the wood grain, the grain inside the crankshaft. Well, a forged crank has grain that's running long ways up and down the crank. It makes it much stronger. I can't break this piece of wood. No matter how hard I try, I can't break this piece of wood. And it's just a little half-inch by half-inch piece of wood. So considering wood and steel, let's think of it like this. Consider the type of wood, the alloy of the steel. And what I mean by that, let's say this was balsa wood or redwood, a very loose grain wood. Boy, I'd be able to break it because it's not very strong. It's not like a hardwood, like a hickory or an oak or an ash. It's not a hardwood. And being that the grain is running long ways in this, it makes it super strong. Let's look at the flip side. Let's say this is a cast crankshaft, okay, and the grain's running a different way. The grain on this one is running this way. It's not running lengthwise. So this is basically like a cast crankshaft where the grain's just kind of going any which way it wants. If the grain's going any which way it wants, it's not running long ways, it's simple. I can break it. It's not very strong. Kind of the same thing with the cast crank. With the granular structure in it not very tight, it's not a very tight alloy. It's not like a oak or a hickory or an ash hardwood. And with the grain going every which way, it breaks real easy. Forged crank is like an oak or a hickory where it's super hard wood, and with a granular structure going the long ways, boy, it's super strong and it'll withstand all kinds of abuse. Well, I showed you earlier about how to tell the difference between a cast crank and a steel crank by the parting lines. There's also another way to do that, which is kind of fun. Now, before I do that, though, let me kind of explain this for a minute. Now, remember, cast cranks, the granular structure is kind of loose and it's not as compactive, so it's not as dense, where a forged crank is really dense. Well, with that, if you take just something, a metal object, and you clank a cast iron crank, because the granular structure of it is not very dense, it absorbs the vibration. Just kind of a clank. If you hit a steel crank, it'll actually have a ring to it because it's so dense and hard. So if you have a steel crank, it'll actually ring like that, where a cast crank won't. Well, talking about forged cranks, just because a crank is forged doesn't mean it makes it good or stronger than another forged crank. What I mean by that is we talked about the different types of alloys. Well, there's also other types of alloys that aren't as good. And just because a crank is forged, what's it forged out of? Forged out of what? And where was it forged? So just like the screwdrivers I showed you, the cheapy little screwdriver that I got for 69 cents, the tip on it lasted no time at all. 3 or 4 screws going into some wood or some steel, and the tip blew off the thing. So that really wasn't a very good quality screwdriver. Well, the next one up had a carbide tip on it. Yes, they're both screwdrivers, kind of like both forged cranks, but one's of a different alloy, so it lasted a lot longer. Of course, the price was a little bit more too. So when you're talking about forged cranks, make sure you're getting a good quality one, because if you get a cheap quality one, you really might not be getting what you think you're getting, and the strength might not be there to withstand what you're going to put the rigors of that motor through. So let's talk about what different cranks cost. Now really, you pay for strength and quality, and also the lightness of the crankshaft and different features of the crank. Okay, but the lighter the crankshaft and the better the quality, obviously, just like tools, the lighter and smaller and better feeling and better quality the wrench is, the more expensive it's going to be. Cranks and internal components of the rotating assembly, they're no different. It's all metal. So on a cast iron crank, you know, your motor probably already has one of those in it. Do you need to step up to a forged or a cast steel? It's a good idea if you're going to put a lot of power to it, but honestly, how often do you see crankshafts come flying out of engines or engines with broken crankshafts? It's pretty rare. So cast iron cranks, they're usually good for 400 plus horsepower. You shouldn't have any trouble with that. To be honest with you, I've seen race motors come in like in Econorails that run 9-second quarter-mile times, budget motors, mind you, but with cast iron crankshafts. Now, mind you, an Econorail is a very light dragster. There's really no weight to it. where if it was in a heavy vehicle and you're putting it under high shock situations, like a manual transmission or a very high stall converter coming off the line with slicks, coming off the rev limiter, and you shock that car off the line as it launches, you're torquing that crank, you're gonna break it. And that's when you need to step up. So cast iron cranks are okay so long as they're not in real high horsepower, high shock situations, especially in a heavy vehicle. Price on something like this, you already have one. You probably get it turned and machined and polished for about $100, somewhere's right in there. Maybe a little more, a little less, depending on a machine shop and the features that they do to the crankshaft. But somewhere's in there, you're good to go. The next step up is a good little quality cast steel crankshaft. Now these run anywhere, around the 150 to 250 area. They're made out of cast steel. They're certainly stronger than cast iron. This is a SCAT 9000 crank. It's an excellent crankshaft. Excellent replacement crankshaft for most stock vehicles and a lot of performance vehicles. It's got good bang for the buck. Not quite as strong as a forged, but a lot stronger than a stock cast iron one. Now you jump up to a forging. Now you start jumping up into some money with some quality ones. This is also by SCAT Industries. It's an excellent crankshaft. It's made out of 4340 steel, and these run several $100s. Forged cranks, whether it's SCAT or any other brand like that, there's lots of them. Eagle, there's Kohler, Callies, there's lots of good cranks out there, and they're going to vary on forgings from as little as $299 for some low-end ones on up to $1,500, $1,600 for a good, excellent quality forged crankshaft. So you have to allow yourself enough budget, just like purchasing tools. If you want a good tool, it's going to cost you some money. If you're going to buy cheap tools, well, you can't expect them to last you a long time or to go through much abuse, but it might get you through to the next year or something like that. Now, jumping up in crankshafts, we haven't talked about this much. I did say billet earlier. This is a billet crankshaft. It's super lightweight. Now, what billet is, we talked about forging, where they take a piece of metal and they hammer forge it together and actually form it into the piece that you want. These are made out of a solid ingot of steel, just a complete solid ingot. Looks like a cylinder, only it's solid. Then they put it on the machines and they cut it all out. There's no parting lines on anything on this because it was one solid chunk of steel. It wasn't forged or anything. It came out of the steel mill with very high-end steel. And then they actually machined this all out of one solid. These are very expensive cranks. Billet cranks usually start at about $2,000, and they can go up over the $4,500 range real fast. They're super lightweight. A lightweight rotating assembly revs faster. It needs to be a lot stronger steel to be able to be smaller and lighter to withstand the kind of strength that it needs without breaking, because it's a lot smaller. You can see these counterweights on here are actually pretty small. There's not much there. Same thing with the rod throws and the mains. They usually put them in race engines that have smaller journals, aftermarket blocks, race blocks and stuff, where the journals are a lot smaller. It takes down on the mass. But you get into cranks like this is hardcore race stuff. You really don't need anything like this in any type of street or street strip vehicle. This is all out road racing, drag racing, stuff like that. Predominantly road racing. NASCAR guys use these. A lot of the road race guys use this type of stuff where they need lightweight rotating assemblies. And we'll get into that a little bit later about the lightness and what that's good for. All right, let's talk about the different parts of a crankshaft. Now, pretty much all cranks have the same different features on them. Okay, you have the snout where the timing gear and harmonic balancer go on. You have the main journals, and this is where it sits in the block where the main bearings ride against. And different engines have different amount of main journals. Some have 4, some have 5, some have 6. Depends on the length of the motor and how many cylinders it is. Then we have what we call the rod journals, or what's also known as throws. Sometimes we call them throws because that's what pushes the pistons and rods up and down the cylinders. And on the backside, we have the counterweights. And the counterweights there just to help offset the weight of the piston and rod on the other side. And we'll get into that a little bit more on balancing, but just a quick view of that. I mean, if you carried a heavy bucket in one arm and nothing in this arm, you got to lean your body over to counterweight it. Well, if you got two buckets of equal length or equal weight in them, you can walk along pretty easily. That's the same thing with this. When we get into balancing, we'll explain that more, but basically the counterweight's there to help counter the weight of the rod and piston on the other side to equal it out so it doesn't wobble. Now, something with cranks also, they all have what's called a stroke. And what stroke means is the distance between the center line of the crankshaft to the center line of the rod throw. And the more area you have between the center line of both of those, the more stroke you have. So a crank with a small stroke is doing this, a crank with a large stroke is doing this. And what stroke really is it makes leverage, okay? And leverage makes torque. And when you increase cubic inches in an engine by adding more stroke to it, that's what we call a stroker, okay? So let's say a 302 Ford has a 3-inch stroke. We're going to make a stroker out of it. Well, what we'll do is we'll add to the stroke of the crankshaft by 400 thousandths. Instead of a 300 stroke, it's a 3.400, almost an extra ½ inch. And that increases the distance between here and the center line of the rod throw, which gives it more leverage, makes it more torque. Torque is what moves the vehicle. A lot of people emphasize too much on horsepower, when really torque below 4,400 RPM, it's all torque that's moving the vehicle. Horsepower doesn't even really come into play until 4,400 RPM and above. So really you want to increase the torque and increase the power of the vehicle from 0 to 60 acceleration is all in the torque. Let me kind of explain torque a little bit more to you too. We'll grab a couple of wrenches here and explain torque and stroke. And what I mean by that is anytime you increase the stroke on a crankshaft, you're increasing the leverage. So that crank is getting bigger, bigger, bigger. It's like going from a wrench like this, just a small little wrench. I can only push so much on this. So let's say I'd have to take a bolt up to 100 pounds of torque. Well, if I tried a little wrench like this, I'm really going to have to pull, I'm going to break my hand trying to pull on this thing that tight to get that much torque. And by the way, I'm going to break the wrench too. So if I went to the next size wrench up, it gives me a little bit more leverage, okay, because if the wrench is longer and I can pull on it a little bit tighter, but still getting to that 100-pound mark, I'm really going to have to pull on this thing. Well, if I use a longer wrench, something like this, I can get even more torque out of it because the distance between where the socket head is at and where my hand is at out here, I've increased the stroke, which makes it much more easy. And of course, I could cheat and get a great big long breaker bar, and that makes it even better yet. You're limited in situations like that, though, with space. Sometimes you can't get a breaker bar in between. Let's say you're taking an exhaust manifold bolt off, and you got a fender well on one side and the exhaust manifold on the other, and you can't get a breaker bar in there. Got the same problem with engines. You can only fit a crankshaft so big inside the block, even as it is, even with 383 Chevys, 347 Fords, and things like that. You really got to grind the inside of the block out to clear the extra stroke in the crank. We can only go so big before the crank has so much stroke that the connecting rods, you have to clearance the inside of the motor so much you end up in the water jacket. So you just can't add that breaker bar sometimes. So there's limitations on the size of the wrench or the size of the stroke that you can possibly put in a motor. All right, so the next question would be, well, how do you get a stroker crank? Well, back in the old days when I was younger, we used to have to make our own stroker cranks because there really weren't any cranks available. And how we did it back then was on the rod throws, we'd actually weld on the outside of the rod throw and then regrind it back down offset. That's what's called an offset ground crankshaft. It's not exactly the strongest way to build a crankshaft, but sometimes when you don't have anything available, that's what you have to do. Of course, these days, there's lots of parts available, and there's cast cranks and forged cranks and billet cranks that are just made for strokers, and strokers are getting really popular. Now, when I was younger, an 1/8 inch of extra stroke was a pretty good amount. These days, you look at that and you're like, that's nothing. But think about this. An 1/8 inch of stroke times 8 cylinders, that adds up quite a bit. Okay, but these days, a good stroker crank, let's take say a 351 Ford. That's a 3.5 inch stroke crankshaft out of the box, right out of stock, okay? When we make strokers out of those these days, I do a lot of 408 cubic inch Fords, and that goes to a 4-inch stroke crankshaft, so that's a 1/2 inch of stroke. And mind you, the torque that these things make is just monstrous, because that 1/2 inch is times by 8 cylinders. So you've increased the leverage on that by quite a bit, so the torque really goes up. Now keep this in mind. Anytime you add stroke to a crankshaft, you add to the mass and the size of the rotating reciprocating assembly, okay? Well, that slows things down. Remember the Japanese movies? You'd see the monsters in the movies and stuff, and the little buildings falling over, and you always went, oh, how fake. That's because they were little teeny model sets and they fell over in real time, and you could tell it was fake because small masses move faster, large masses move slower. When we're dealing with crankshafts and you increase the stroke and the size of the crank, it's going to move slower because it's a lot more mass. Well, I get a lot of people calling and saying, hey Aaron, I want my motor to rev to 8,000 RPM. You're not going to build a stroker to go up that high because you've increased the piston speed going up and down. Every time that crank makes the same rotation, 360 degrees, the piston going from the top of the deck on down to its lowest point and back up again is traveling a greater distance, so the speed increases. Well, sometimes that's good situations, sometimes that's not. It just depends. It has a lot to do with fuel burning also. You need different types of octanes of fuels and different burn rates because the piston's traveling at a greater speed. The fuel inside needs to burn at a different speed also. But talking about revving, now a lot of people say, hey, I want that engine to rev to 8,000 RPM. Well, one thing that's kind of dumb these days, because most engines with the types of heads that we're using and the camshaft profiles, even in all-out race motors, they peter out at about between 55 and 6,500 RPM. We're not in the old days anymore where you really had to rev the living crap out of a motor to get anything out of it, okay? But let's think about revving an engine and what that has to do with anything. Two-stroke motorcycles rev really high, and they run really strong when they're up on the pipe or on the power band. Below that, below the power band, they're really not very powerful, especially if you have a passenger on the back. You're riding a dirt bike, a two-stroke dirt bike, and you got someone on the back and you're going to try and climb a hill. It'll do okay as long as that thing's at 18,000, 19,000 RPM and up on the power band. But if it's below that, it's going to fall on its face, or if you upshift too soon, that poor bike's going to stall out and fall on its face. Take a four-stroke bike, though, like a big thumper, say the old 500cc single-cylinder thumper bikes. Man, just pop, 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 right off an idle, that thing will just climb that hill. They're almost like a diesel motor. They're so torquey. They don't need to rev very high. In fact, you can do a third-gear wheelie right off of a dead start on one of those things, or put two passengers on it, and that bike will climb that hill, no problem. Engines are the same way. It's not necessarily how high it revs, but how much torque it has to pull that vehicle or that weight along. So we're really not in the old days anymore of having to rev. The stroke is pretty much where it's at to move that vehicle. Let's talk about some of the advantages of adding or taking away some stroke. When you add stroke, you increase the bottom end torque. Okay, well that also in stock vehicles, you usually don't have to lower the rear end gears. You can run a taller rear end gear, and you can run a stall converter with less stall RPM in it also, because it'll just pull right through that. Where if you decrease the stroke, where you take away the stroke from the crankshaft, you really need like the two-stroke bike. You got to have real low gears in the back and have more gears available. You have to have higher stall speeds or have a 4-speed with or a 5-speed with low first gear and low second gears, because the motor needs to get up to its power band. Well, if it can't get up there while it's getting, let's say the power band comes in at 6,000 RPM. You need to get through 2, 3, 4, 5 to get to that RPM. Well, in the meantime, while you're trying to wind the motor up through these benign or inert RPMs to get up to where it's going to make its power at, the guy next to you with the big stroker, he just went right on by you, and he's already 6 or 8 car lengths in front of you. He's long gone. And you're sitting there waiting for your car to pull, 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 pull. Then it hits its power band at 6,000 RPM and takes off. By that time, that guy's already gone. He's already down the track and already went through the finish line. So especially in a heavy vehicle, you really want to increase stroke. So if you've got a heavy vehicle and you haven't changed the gears in the back, or you haven't put a high stall converter in it, a stroker motor would be ideal for you. If you've got a lightweight little vehicle with some low gears like 411s or 456s in the back, and a 4-speed or an automatic with a 3500 or 4500 stall converter, a little small high winding motor can do good too. Some guys like the small motors to wind up high, and they have fun with those. Okay, so let's think about that though, and decreasing the stroke. Chevy did that on some of their early Z28s. They took the 327 and they had a bunch of leftover blocks and cranks and stuff, so they took the 327 crank out and they put a 283 crank in there and dubbed it the 302. And the 302 with its little 3-inch stroke, that was a 1/4 inch less stroke than the 327s. And that was our notoriously high winding engine. Those things would see 8,000 RPM all the time. They were notorious for that. They would do that because the rotating mass inside was so small they could do that. If you take a big stroker like this crank right here is for a 545 cubic inch big block Ford. Okay, we build a lot of things like this. You ain't going to take a 545, especially with a cast steel crank like this, up to 8,000 RPM. It'll just blow itself apart. The centrifugal force kinetic energy in that is so much it can't contain it and things will come apart. So there are times when you want to decrease or increase stroke. All right, we talked about the general features of crankshafts having all common features. Let's talk about the features that an aftermarket crank has and what you're paying for when you buy an aftermarket crank. Now, first thing is on the counterweights. If you look at a stock crankshaft, the counterweight facing area is flat. Now, this is the area that goes through the oil. Okay, and the crankshaft goes through the oil and it slings it up onto the camshaft, and that's what oils the underside of the pistons and the rods, not the rod journals themselves because that's pressure fed through the crankshaft, but the wrist pins and cylinder walls and the camshaft all get oil solely slung off the crankshaft. None of that's pressure fed. So these are flat. When you come over to an aftermarket crank, they start rounding the corners out a little bit. This one's slightly rounded. Okay, when we come over to a really killer crank, They're what they call knife-edged. If you look at this, it comes right up to a point. Now you say, well, why would you want to do that? They sling oil. Well, it'll still sling oil, but the difference is anytime a crankshaft goes through oil, it has what they call a parasitic loss, and you lose horsepower. What that means is the oil is actually robbing the engine of horsepower as the crankshaft's going through it. Let me give you an analogy of that. You're sitting in a swimming pool, and you're in so deep of water, okay, or so deep of water, and you're just kind of there waiting around. Now take your hand flat and go pow into the water and try and force it through. One, it's going to hurt because your hand slaps the water, and as you go through, you have the force of the water pushing the flat part of your hand through. Now, simple, take your hand sideways and plug it through that water. It'll go poop right on through, like a hot knife through butter. Much easier, much less effort, much less noise, much less disturbance to the water. Took less effort, same thing with the crankshaft. Takes less effort, robs less horsepower. So that's one of the features. The next feature is, you look at a basic cast iron or steel crank, or cast steel crank anyway, they're just a natural color. They're not colored or anything. You look at one that's what they call nitrided, and it actually has a beautiful gray color to it. We look at this one down here. This crankshaft is nitrided, and it's a beautiful smooth gray color. And that's not the natural color of the steel. Steel is obviously usually shiny. Nitriding actually hardens the crankshaft. Not just the actual alloy of the metal is just hard, but what they do is they put it through a heating process where they heat that sucker really hot. I mean, where it's white hot, and then they do it under controlled cooling. And what they also have shallow nitriding and deep nitriding. Now the nitriding on most levels goes down 5 or 8 thousandths of an inch, somewhere's in there in a crankshaft. Some go as much as 10 or so, but nitriding is just a very thin layer of hardness that it does on the crankshaft, and it gives it this really nice finish color. So if you have a crank that's a natural finish, such as one of these or one of these, it's not nitrided. If it's got a beautiful gray finish to it, then it's nitrided. Now another feature on crankshafts, aftermarket cranks, back when I was younger in the olden days, we used to do what's called cross drilling. And cross drilling a crank, if you were running a race engine and you had a cross drilled crank, you had something. Okay? What we didn't know is that we didn't know what the heck we were talking about. Cross drilling a crank doesn't work. And I'm going to show you what it is. This old crank right here, this is just an old crankshaft that came out of an old motor. Who knows? I got hundreds of them around here. We don't know what this came out of. This is just a standard 302 motor, 302 Ford motor. Someone had cross-drilled it. And what cross-drilling is, it's the oil galley holes that come up when the oil pump is pumping oil through the motor. It goes up through the block and it comes up through the mains and it feeds the main bearings. And the main bearings, there's oil holes in the journals here that pick up the oil and it routes it in through the rods and it goes all through the crankshaft. Okay? This is what keeps the bearings lubricated. Okay? Well, a cross-drilled crank, and the way you can tell if your crank is cross-drilled is it means you can put something in there and go straight through the journal. This is cross-drilled. What this allows is oil to come in on one side, and on a half a revolution, as it comes in the other side, it oils the bearing on every half revolution. That all sounds great in theory, and there's a lot of things that work great in theory, and in reality, it just doesn't work. And the reason that worked good in theory is, it gives the bearings more oil. It gives it oiling every half revolution, not all the way around every time to pick up the oil. Okay? Problem is centrifugal force, kinetic energy and centrifugal force. At 6, 7, 8,000 RPM, what happens is what we call a pinwheel effect. And what that means is the crank's spinning so fast, the centrifugal force inside the journal there throws the oil out to the side and it actually robs the rod journal of getting oil. And you say, well, how does it rob the rod journal? Well, the rod journals are getting fed by the main journals. Oil comes in, when it comes out of the block and comes into the bearing area, it squirts up and you can see it plainly comes right on through and feeds the rods. And all these do that. They come in at angles. So every main bearing is being fed through the oil galleys in the block and it's feeding through here up to the rods, and that's what oils the rod bearings. The only thing keeping main and rod bearings from seizing up or welding themselves together is that thin layer of oil inside keeping it protected. Well, the problem with cross drilling was we used to lose cranks all the time going, man, I don't understand it. It must be the oil or it must be this or that. I've got to increase or decrease clearances or increase clearances and stuff. What it was kinetic energy, or the centrifugal force of that crank spinning around. It slung the oil out to the sides, kind of like the energy if I put water in a bucket and I swing it around, it stays. If I go fast enough, if I go slow enough, I'm going to get doused with water. But if I go fast, I keep it around, that water will stay in that bucket. Same thing happens in the crankshaft. It actually starts drawing the oil away from the rod bearings with that pinwheel effect we're talking about. It pulls the oil out. the oil pressure isn't enough to force it through any farther, so it starves that bearing to rod bearing. You end up losing rod bearings and pitching rods, and that was a problem we used to have. These days we don't cross-drill cranks anymore. We got wise to that and said, oh, don't do that. We're having troubles with it. So it's very rare these days that you see a crank cross-drilled. Now there's another way you can lose or gain power just by the crankshaft alone or the rotating assembly alone. It has nothing to do with anything else other than what's called windage. And what that means is, we've already talked about the oil, about the knife edge throws going through the oil, and it's easier to turn your hand on one side as it is to be flat. Well, the same thing as a crank is dipping through the oil, as RPM comes up, if you can pull the oil away from the crankshaft. Now, a lot of times you probably heard the term windage tray. And what that is one of these little guys. And what this does is this mounts on top of the main caps. After the crank and rods and everything's put in, there's, on the main bolts, there's studs, and they come through these holes right here, and this thing will sit down right over the top of the crankshaft. Now the trick is, when these are mounted on, they're adjustable for height. And the trick is you want to get as close to the crank as you can without touching, or the connecting rods also, to allow it to spin. Okay, and as the crank spins at RPM, it slings the oil off. Well, the oil is sitting in the bottom of the pan, and the oil pump is down there. What it does is all the oil draining back through the back of the motor and all the oil sitting in the oil pan stays off the crankshaft. And it's just like you. I mean, if you got wet clothes on, it's harder to run than if you got dry clothes on, because you're not taking all that extra baggage with you and all the extra water weight. Same thing with the crankshaft. So we want to try and keep the oil off the crank at higher RPM. This can be worth sometimes anywhere 10, 15, 20 horsepower sometimes with just a windage tray. It just depends on the size of the crank, how much oil it's sitting in, how much oil you have in the motor, little things like that. Another really good analogy to that, think of it like this. Imagine yourself at the beach and you're riding through water that's ankle deep. Not a problem, you just cruise right along. Now try and run in waist deep water. You can't, man, you can hardly move. Do you think it's easier for the crankshaft to swim through oil that's only this much on the crankshaft, or do you think it's easier for the crankshaft when it's going through an inch or two of oil? So the windage tray pulls that off, and it makes the difference of it running through ankle deep or waist deep oil. And a quick tidbit, a lot of times you can leave your oil pan a quart and a half or so low than what's normal and gain horsepower. Sometimes that's worth 5, 8, as much as 10 horsepower just by being a quart low. And you got plenty of oil in there in most incidences, especially if you have an aftermarket pan that's 8, 9, 10 quart pan. You can run those back a little bit and it keeps the oil level low off the crankshaft. Now there's other ways to do this too. It's what's called a crank scraper. And this mounts right against the oil pan rail. So after the windage tray is put on, this mounts where the oil pan gasket goes on. And basically what it does is as the crank comes around, it fits the rod throws. You hand fit these. They come as a basic design. They're already generally cut out. And then what you do is you put this on, you rotate the engine, and when a throw hits it, you mark it a little bit, you pull it off, come over and file it a little bit, and pretty soon you get this thing where it's really close in here, and as the crank comes around, it just scrapes the extra oil off, and that's more parasitic loss that you can get rid of and get the weight off that crankshaft, and it'll help the motor spin up in RPM faster and make more horsepower because there's less drag on the crank. The downside of this is, in a street motor, this is where some race stuff doesn't work on the street. In a street motor, you're idling a lot. Race motors are not. They're at RPM most of the time. Street motor, they're not at RPM. What I mean by at RPM is up in the power band, 5, 6, 7, 8,000 RPM, or sometimes more. So on a street motor that's idling a lot, or at lower RPMs, 2,000, 2,500, stuff like that, this isn't the ideal situation because it robs all the oil off of the crankshaft that's throwing it up on the cam, on the cylinders, into the wrist pins of the pistons and stuff like that. And if you're at low RPM and it's scraping all that off, there's really not a lot of oil to sling off. So again, for every give, there's a take. And for race situations, this stuff works real good. For street situations, a windage tray is okay, but crank scrapers and stuff, I'd leave that to just the race motors. Now another feature that some aftermarket cranks have, for supercharged engines, on the snout of the crank, will have dual keyways. Now all cranks have at least one keyway, and that's what locates the timing gear on the crank and also the harmonic balancer. But this little key right here, the load, because the front of the crank, the harmonic balancer or the hub that's on there is what's driving the blower. Well, blowers have drag on them. And when you got a snappy engine or a large blower that's putting out a lot of boost, the drag increases. Well, what'll happen is it'll shear that keyway off. So a lot of times we'll go ahead and cut on the opposite side an extra keyway Some aftermarket cranks come with those, so that's just an extra added feature that you're looking for if you're getting a supercharged engine. Well, we already talked about parasitic loss and power loss as the crankshaft slings through the oil. Okay, well, it also does that just from the actual weight of the crankshaft. I mean, a heavier object is harder to move. It takes more power to move that heavier object. So it has to overcome its own weight first before it can start making power. So a lighter crank actually yields a little bit more power than a heavier crank. Now, the way a crank is lightened, you can tell on some, the rod throws on this one are solid. If you look at this one over here, they've been drilled out. That just removes a little bit of weight on that. There's a lot of ways to remove weight from cranks. You can make counterweights much smaller. They back cut the counterweights, not just in smaller in diameter, but they'll back cut them. There's many ways to take weight off. The problem is, though, sometimes lighter and smaller is not as strong as something that's big, thick, and beefy. So you got to be careful of that. Now, a big, thick, beefy crank, yes, it's heavy. It's usually pretty strong. So there's always a give for a take in pretty much anything, especially rotating assemblies. Now, let's think about that weight for a second. Let's say we have two identical engines and they're in two different types of cars. So the identical engine, say it's a 300 horse small block, and you got one in a 2,500 pound car and you got another in a 4,500 pound car. Guess which one's going to be faster and be able to pull a hill better? The lighter vehicle, because that engine doesn't have to pull that much weight. Same thing happens in a rotating assembly, and that's how it makes its power with being lighter and being able to rev up faster and get to its power band much sooner. Another way crankshafts are lightened up and actually strengthened as far as running wise are the bearing sizes. Now, believe it or not, bearing size has a lot to do with it. I mean, the larger the bearing, the more surface area it has. And think of that, well, that's good because it carries more of a load. It also has more friction. And it has a larger bearing, also has more bearing speed. So we want to decrease the bearing speed. Well, how do we do that? We can make the throws and also the mains much smaller. And the reason we do that is, one, it cuts a lot of weight off the crank. I mean, if we can cut 1/8 of an inch off of each throw right here, times 8, that's an inch. Well, how much is an inch-long slug of this particular metal going to weigh in your hand? That's a lot. Spin that at 8,000 RPM with kinetic energy added to it, that's a lot of weight. Okay, so let me kind of give you an idea here. These are both small block Ford cranks. This one's a stock one, this one's a billet one for racing. You can see on the size, this one mics up, there's the size of that one right there. Come back here, same small block Ford crank. Look at the difference right there and how much is taken off. This crank is not underturned. This is just the natural size of a billet crankshaft designed for race purposes. Slower bearing speeds means less heat friction and more ability to stay alive while it's spinning at high RPMs. All right, now we're going to talk about the weak parts of cranks and the parts that cause the most crank failure. And what that is, there's two usual spots on crankshafts that cause failure. The first one is the radius. And what the radius is when you come down here, here's a rod journal right here. And on the journals, if you look at this little area right here, there is no radius area there where it goes from the journal into the throw area, okay, into the arm, what they call the arm or the throw. It's just a straight cut right there. Let's look at an aftermarket crank. You come up here, and this is a stronger crankshaft. If you look, there's actually a really nice beveled edge right there. That's the radius. Most crankshafts have 120 thousandths radius. Some crankshafts, race cranks, have 140 thousandths. But usually a 120, what they call a 120 radii, that's what they're talking about, is this area right here. It gives it more area to withstand the stresses and rigors of the throw going around. Now, some people will say turning a crankshaft, that means machining this area down. Like say the crank got damaged or you got 100,000 miles on the crank or whatever and you machine it down, 10 under, 20 under, 30 under. Some people say that weakens a crank. That's really a bunch of BS. The throws and the main journals are so big and thick, 10 thousandths. Let's say you take 10 thousandths off a journal. That's only 5 this side and 5 this side. So it's really 5 off the surface area. But because it's a circle, it's 10 thousandths. 5 and 5 is 10. So really that amount doesn't really take any of the strength away from the crank. What you can do by turning a crank under, especially on a stock crank that doesn't have a radius, is now when you turn it under, you have the opportunity to grind in a radius and actually create one, which actually strengthens the crankshaft. Now, other areas that cranks break at are what's called stress risers. And what a stress riser is, if you look down here, we talked about cast cranks have the casting parting line right here. Well, if you notice, even on the throw right here, there's an edge that sticks up right here, just a little, sticks up, just a 1/16 of an inch. Well, that right there is a stress riser. If we look over here on the throw, there's even little stress risers sticking up off the counterweight right here and off the throw. Now, these little areas can cause points of interest for tearing. And let me kind of give you a scenario of that. If we take just a piece of cardboard right here, I'm just going to make it really simple. If I have an edge, which is like one of these stress risers sticking up, and we start flexing the crank or twisting or something, this little edge right here acts like a stress riser that's on the crankshaft. Well, it's easy to tear. Okay, really simple. If we round that off and smooth it, say we take a grinder to it, like a die grinder, you can do it in your home with a die grinder, and take those casting flash off, what they call casting flash or stress risers, you remove those and round the edges. Well, just like this, if I fold this in half, now this edge is rounded, it's harder to tear. I have a hard time tearing it. Okay, so it's easier to tear an edge than it is something that's rounded off. So if we look at this aftermarket crankshaft, you can see that they've removed all the stress risers on here. There's hardly any stress risers where the parting line was. And trust me, on a forged crank, this is an okay example, but like factory forged cranks, the parting line, the wider parting line, they're actually raised up a 1/16 or an 1/8 of an inch sometimes. And you can even take those off as stress risers too. Grind them down smooth. This crank has already been ground down a little bit from the factory before it was nitrided and everything. But by removing those stress risers, it doesn't give a place for a crack to start forming. By rounding it off, it just eliminates the risk of cracking, basically. Well, while we're on the subject of radius on the rod throws and stuff, let me just explain something real quick here. We'll get into this later while we're talking about bearings, but while we're here, I'll just tell you about it. Crankshafts that have a 120 or a 140 radii on the rod throws use a special bearing, and that bearing has a chamfer on the edge, where a stock bearing does not. But if you look, this has a chamfer on one side, and this side goes against the radius on the crankshaft to give clearance. Otherwise, what will happen is you put the rods on, you torque them down, and the motor won't turn over, won't spin by hand or anything because you've wedged the edge of the bearing, the squared off factory rod bearing against that radius. So anytime you use an aftermarket crank with a good radius on it, you're going to need bearings like this that do have the radius on one side. All right, if you're going to have your crank out and you're going to do a quick rebuild on your motor, and sometimes some guys will say, oh, the crank looks good, we don't need to turn it or have it polished or anything like that. It looks good. Or it's kind of so-so, but you'll polish it and it just takes out little tiny imperfections. Now, just because it looks good, or if you take a micrometer and mic it and it mics pretty good, that doesn't mean the crank is good. You can't tell by looking at it, and believe it or not, it's hard to even tell by miking it sometimes, just because of two factors, roundness and taper. Okay, you could have taper in the journal. One side wore a little bit more than the other, and also roundness. And when I'm talking about roundness, you say, well, gee, Aaron, we mic'd it, it's round. You need to mic it in several places. You need to check it this way, check it this way, check the edges, check both sides, all around on all the journals. Because it can wear a little bit more on one side than the other, or it wore on one journal. Mind you, there's two connecting rods on this journal. Maybe one wore a little bit more than the other one, and it still could be smooth. And you might not notice the transition from side to side. So you look at it and you go, wow, that looks great, and we polished it up or took a little emery cloth to it, which is an old trick that a lot of guys used to do in the old days, or a little Scotch-Brite to clean up the crank. That's not a real good idea. If you're going to polish a crank, send it out and have it professionally polished. Because anytime you rub on it with emery cloth or Scotch-Brite, you're removing metal just underneath your fingers. You're actually putting two little grooves in it. You can't really get it straight like that. Have it polished professionally. But really mic the crank good, and you want to double check it in several areas. Because like I say, it could be tapered or out around, and you're going to wonder why your bearings failed in a real short amount of time, or why you had oil pressure problems. Also, you want to be sure there's no nicks or scrapes or gouges of any kind. If you can catch your fingernail on it, some guys will feel it and say, oh, I catch my fingernail, it's time to turn it. It might be time to turn it even if you can't catch your fingernail on it. Rule of thumb that I go by, if you take the motor out, take the crankshaft out and you're going to rebuild the motor, go ahead and turn the crank anyway. Just start from fresh. Do it once, do it right, and be done with it, rather than mess around, because you're going to try and save, what's it cost to turn a crank? Between $80 and $150, really. It's nothing. In fact, $150 would be on a real high side. It's really right around $100 or so to get a crank turned and have it all polished and the oil holes all chamfered up and everything real nice. It's not worth that to lose the entire motor over just to save a couple of dollars. So in a nutshell, what have we really learned about crankshafts? That there's many different types and sizes and shapes and stroke and you name it. We learned that basically A cast iron crank or a stock crank is good for up to 450 horsepower in some instances. If you're going to go blown or nitrous or any type of race use, then for sure a forged crank is the way to go. And it's worth spending the money on that to avoid engine failure. And if you're just an all-out racer, you're going to be spending super high RPMs, then something like a billet crank if your budget allows for something like that. All right, this segment we're going to talk about connecting rods and all the different types of connecting rods and what they're used for and everything you wanted to know about connecting rods. So we're just going to go right on down the line here and just take a whole series of them. The first one right here is a cast iron connecting rod. Now, very few engines ever came with a cast iron rod. Most rods in most engines, most Fords and Chevys and Chryslers, a lot of those, had forged rods. Some had cast rods, though. Very few, but some. The way you can tell a cast iron rod is just like on crankshafts. If you look at the parting line, it's a very, very thin parting line. If you look at it real close, it's almost stipply looking, just like outside of a cast iron block or looking like a cast iron crankshaft. It's stippled. That's just because of the way the granular structure is in it. Okay. Next rod up is a stock rod. This is one of the new rods. This is made out of powdered metal. It's actually powdered metal that's just compressed together. So it's kind of a cross between a forging and a casting. They're kind of a new technology. Powdered metal rods tend to be pretty hard. These do have casting flash on them, though. If you look at it, you can see along the side here, we talked about that in cranks. If you wanted to strengthen the crankshaft, you could polish those off and relieve the stress risers and casting flash. It makes the rod a little bit stronger. If we go to the next rod, this is a typical Chevrolet everyday rod, a forged rod. And what people don't really realize about Chevy rods is that almost all of them are forged. I can't think of a small block Chevy that actually had a cast iron rod in it. On a lot of the Chevys, though, you get guys buying what they call the Chevy pink rods. And really all that was just a stock rod, except it was magnafluxed. And what they do with magnafluxing is they're checking for cracks. It really wasn't a different series of rod or anything like that. They came in Z28s. You used to be able to go to GM and buy the aftermarket, or not aftermarket, but the performance pink rods from Chevrolet. It's just assured that they weren't cracked. Now this actually is a rod that was run in an early race motor. I save a few things like this around the shop sometimes to show people. And someone has actually polished the beams on it. They've taken all the stress risers off, and that's what it looks like when you polish a beam. But it is just a standard Chevrolet forged rod. We'll go to the next one here. This is one of the new aftermarket rods. This is a scat rod. These are made out of 4340 steel. Some rods, Eagle has some that are made out of 5140. That's the alloy of steel. It's 5140 or 4340. They're two different types of chrome moly. Very good steel. Very good bang for the buck on these connecting rods. These days, for what it costs to remanufacture a set of factory rods and putting good bolts in them, like ARP rod bolts or anything like that, and resizing them and doing both ends and stuff like that, by the time you pay for all that, you could have bought a brand new set of aftermarket rods that are a better alloy. They're lighter, they're stronger, they're just a better way to go. And of course, these are forged. Easy way to tell they're forged. It has a wide parting line, and it's not quite so stippled on the outside. Now this one here has a different feature that some of the new rods have. It doesn't have a stud and a nut like most rods have, like most stock rods have. In fact, if we look at this one right here, we can see it's a stud that comes through with a nut on the end. These right here use what's called a through bolt. So it's actually a bolt that's actually threaded into the upper part of the beam part of the rod. Stronger design that way. And this one also is designed for full floating wrist pins. And when we get into pistons, we'll talk about that. But full floating wrist pins use a bushing, a bronze bushing on the small end of the rod. And that way the wrist pin can float around inside there. You don't have to press them in through the piston and through the rod. But you can tell, easy way to tell that is if it has a bushing or if it doesn't. If we look at a standard connecting rod, there is no bushing in here, it's just the steel. And we'll talk about that when they talk about how to install wrist pins into connecting rods. Now the next one up is a forged H-beam rod. And what this is 4340 steel. It also has a bushing on the top because most performance engines like this and race engines that use this type of rod are almost all using floating wrist pins. It has giant 7/16 inch through bolts like this that go through the big end of the rod. Super strong rod. Rods like the I-beam rods such as this one here, these are good for up to about 500 horsepower. Stock rods, I've seen stock rods in engines with 500 horsepower, and I've seen them last. You're on borrowed time, though. I mean, I wouldn't really recommend it. If someone said, hey, Aaron, build me a 500 horsepower motor, I wouldn't be sticking stock rods in it. I'd certainly go with aftermarket set. But if someone said, hey, Aaron, I got some money, I want you to build me a 500 horse motor, even though these will handle up to 500 horsepower, the key word is up to 500 horsepower. I really wouldn't stick these in something making 500. I'd rather go with something that can handle 750, 800 or more horsepower and run a set of these types of rods. Now, we talked about this in crankshafts and the granular structure and the way cast rods and forged rods are, the way the grain runs. And the grain in these is running long ways. You want this beam to be strong so it doesn't twist or bend or flex or anything like that. And I'll use that same analogy again, just like wood. A lot of you are familiar with wood, where the grain ran long ways. Well, just like a connecting rod, you can see the grain in this is running long ways, just like the grain in a connecting rod runs long ways. Okay? Well, in forgings, it actually aligns the grain up. In casting, it doesn't. They're just random. So with the grain running like this, if this is a long way of the rod, I can't break that. How much pressure I put in this, I can't break it. If I had one with the grain like a cast rod, here's a cast rod, and with the wood like this, the grain's running crossways. Well, in a cast rod, grain's going every which way. It's not in a controlled direction. So with grain running crossways, just picture this piece of wood right here as like the rod beam. You're at RPM, you got a lot of load on it, a lot of horsepower, and a lot of forces being put on that rod, and guess what happens? Breaks. Okay, so a forging is a little better way to go, or definitely a better way to go for high horsepower applications. Now the other one down here, the last rod I'm showing you here, is an aluminum rod. You never want to run aluminum rods on the street. Aluminum rods, they are super light. Mind you, for aluminum to be the same strength as steel, it has to be a lot thicker because it's not quite as strong as steel. It takes a thicker amount of aluminum to equal the same amount of steel. But they are much lighter. This is a super light connecting rod. This is used in real high horsepower drag race engines. Now some guys say they'll run aluminum rods on the street. Got news for you, aluminum fatigues. And when a rod fatigues, it will break. And you can't see fatigue. It might look like a perfectly good rod, might not have any nicks, cuts, or scrapes in it or anything like that, but it's fatigued and it will break. Typically, an aluminum rod will last, a season. Some guys will try and get 2 seasons out of them, but really they're only good for a season. Now here's a no-no with aluminum rods. You can go to swap meets, and a lot of guys will have aluminum rods out there for sale, cheap, $300 for $200, or sometimes even $100 for a set of aluminum rods. Like, oh, I only got 1 season on them. They're boat anchors. Don't buy them. They've already got a season on them. They're already fatigued. They might look okay, but they're not. Don't waste your money. I mean, unless you want some paperweights laying around the shop, some cool paperweights, you can also make some cool things out of rods like this too. I've seen guys make paper towel holders and toilet paper holders and all kinds of cool things out of old rods. But I've even seen steering column supports on street rods made out of connecting rods. It looks really cool. But that's all these things are good for. So don't waste your money on that. All right, well, I mentioned pressed pins or floating pins. Now we're going to kind of show what that's about. Now on a connecting rod, here's a wrist pin out of a piston right here. Now on a stock connecting rod, they're pressed into the connecting rod, so it really won't fit in there. What has to be done is this needs to be heated up in a furnace. And then we put the piston and rod in together and we slide the wrist pin through. Okay, then as the rod cools down, it grabs and locks onto that wrist pin and holds it in place. That way it can't slide out one side or the other of the piston and damage the cylinder wall. Now floating pins, it just slips right on through. It's bushed and it'll actually slip in, so it actually glides in and out. What holds it in place are lock rings on the piston to keep it from sliding out one way or the other, but it actually floats around on here and is just a better design for serious performance applications. And we're going to talk about why connecting rods fail. Now, I've heard a lot of people say, oh, I threw a rod or I pitched a rod out the motor, must have been weak, and that the rod broke at the beam. And I did show you about the granular structure and where the grain goes and about how the beam can break or how any type of metal can break if the grain's not going the right way. Well, on connecting rods, it's really not the beam's fault when it breaks. 90+% of rod failure is because of the bolt. The weak link in any connecting rod is the bolt. On stock rods, the bolts have a fairly low tensile strength, and that's the only thing clamping the cap on the bottom of the rod are the bolts. I mean, the only thing holding the whole motor together are the bolts, so the bolts had better be good. So you want to be sure that you got good rod bolts. And what happens is when you have a connecting rod and it's going up and down the cylinder, what happens is the bolts begin to stretch. They can't take the energy because it's not just the downforce. When the piston is being pushed down, the load is on the top side. It's pushing on the crankshaft. When it comes back up and hits top dead center, okay, it's pushed out the exhaust. All right, now it's on its way back down to suck in new, fresh, clean air. Well, there's no load on top of the piston. What's happening is it's gone from an upward motion to a stop to a downward motion again, and the crankshaft is just ripping on this rod cap right here. It's pulling on it, and you got the weight of the piston. Well, the heavier the weight of the piston, the harder it's going to push down because it happens in a nanosecond. It goes up, bam, comes right back down, and it happens faster than you think it does. Well, obviously, the heavier up here it is, the more harder it's going to push down here. What it starts doing is pulling on these bolts. As soon as the bolts start to stretch, the cap begins to walk a little bit back and forth. The bearing inside gets a little bit loose. It loses its shape, and it spins inside, and it starts spinning the bearing. What happens with that? It eats the crankshaft up, it eats the connecting rod up, and pretty soon the cap comes off. This is happening in all this amount of time. The engine's probably turned over another 100 times. Just in a few split seconds, it's already gone up several times, up and down. Well, what happens is the piston comes up, and it hits on the very last stroke. It comes up, hits, and when that cap can't take anymore, it goes to get yanked down, the bolts just pull out. So what happens is it leaves nothing there. The crankshaft comes back around one more time because you got 7 other cylinders still turning that crankshaft. The crankshaft comes up, hits it right here, and guess what it does? Throws it right out the side of the block. And as it does, it stretches and pulls on this beam, and it breaks the beam. So when you're looking at a rod, you're like, whoa, it broke the beam right in half. No, the bolts failed. Bolts usually fail because either they're not strong enough or they were old and they've been torqued for how many years, and you can't tell by looking at a bolt how strong it is. You can look at this one right here and say, wow, there's nothing wrong with this bolt. Well, maybe that bolt's got 50 races on it or 10 years of racing. How do you know? Or maybe it hasn't had any years of racing, but it's been torqued in this rod for 10 years at 70 foot-pounds of torque. So it's been stretched. Anytime you torque on a bolt, you stretch it. And that's what clamps it together. And that's why rod bolts, main bolts, things like that inside of motors don't use lock washers. You're relying on the type of material it is and the amount of stretch the bolt has to keep its clamping pressure. Well, after years of being stretched, a couple of thousands, average rod bolt stretches 5 to 7 thousandths. Somewhere's right in there. Usually around 6, somewhere's in there, 5.5, 6 thousandths. But in that given range, that bolt's been stretched all this time. After a while, it loses its slinkiness, and so you torque it down to size and think, oh, that bolt looked fine. You torque it down, yeah, but it was fatigued. So now you go taking your motor out, you go racing, it pitches a rod, and you go, oh man, I broke a rod. It's because of the bolt. The way we can tell if a bolt is good or not is when you get new rods and rod bolts, you check them with a bolt stretch gauge. This is a rod bolt stretch gauge. And what we do is we put the bolt in there, and we take a measurement of it when it's new. Okay? Then we put it in the rod, and what we do is we start torquing on it and finding out where we want our bolt stretch. So what we do is we put it in a rod, we'll put this in a rod vise, and we'll start torquing on it. All right? And the rod bolt company will say, you're going to need 6 thousandths of stretch for that rod bolt to have perfect load or perfect torque or stretch. So 6 thousandths is what we're trying to achieve. So what we do is in the rod vise, we torque on it and check it, and we'll put them in and check it. And we'll torque on it some more, check it, until we get our 6 thousandths, and then we say, okay, that was 64 foot-pounds of torque. That way it kind of self-calibrates the torque wrench too. And then you know, okay, 64 foot-pounds is what this is going to need to achieve the correct stretch, which puts the correct preload on that rod bolt, so it assures that the bearing's going to stay in place. If a bolt starts stretching, it gets longer when it's in its relaxed state. So say we've run this a few times, we keep a log on that on race motors, and we'll go back and check it again and go, hey, this bolt's 3 thousandths of an inch longer than it was when we first started. That bolt's been stretched, it's done. Get rid of it, buy a new set. They're cheap. It's cheap life insurance. Now, another way we can get bolts to be mistorqued or the bolts to break is from improper lube. Now, consider this. You have threads going into steel. So you've got a steel bolt going into a steel rod, and you've got friction on the threads. Now, when you torque a bolt, let's say the bolt has 10 foot-pounds of frictional value to it as it's going into the threads, okay? And then you say, okay, I'm going to torque that bolt to 60 foot-pounds, and you torque it to 60. It's really not, it's really 50, because you've got to fight against the friction that the threads are creating. Now, different lubes have different frictional values. Now, a lot of factory motors, they say, oh, torque the bolt to 45 foot-pounds with 30 weight oil. Okay, well, that's fine. But most race rods and performance rods, we use a high-grade ARP bolt. And the ARP bolts, they recommend using ARP lube, which is a moly lube. And it's a different kind of moly than what we use for engine assembly lube or the mollies that you use in like your wheel bearing grease and stuff like that. This is a specially designed formula for rod bolts and for main bolts. And it has a very low frictional value. So, for instance, the rod bolt, if you look at the instructions that come with the rod bolts, it'll say, with 30 weight oil, torque it to 75 foot-pounds. With ARP lube, torque it to 55 foot-pounds. Sometimes there's a 20 or 30-pound difference, especially on main bolts, but rod bolts, sometimes there's a 10, 15, 20-pound difference, and on main bolts, I've seen as much as 35 pounds difference just in the lube. So you can't just go by a torque wrench by what that says, because you have to take in consideration the type of lube that you're using for the type of bolts. And a mistorqued bolt is also an unstretched bolt, and it's not stretched to the right value, it won't clamp its force. Now, on the opposite end of that is over-torquing something. You overstretch that bolt. Now it's really stressed and it's just ready to break. That's also not a good scenario. It needs to be correct, and that's the key to a long-living motor, especially at high RPMs or under high horsepower conditions. Now, there's many different types of rod bolts. There's different alloys, different strengths. I mean, there's different features of rod bolts, too. It's not just go out and buy a different set of rod bolts and switch them out. First thing to know on a typical rod bolt is they have a knurled area right here. And what that is when you press a rod bolt into a rod, it actually, the knurling actually bites into the rod. Well, guess what it does? It creates stress risers. And stress risers, well, that's an internal stress riser. It's a place for the rod to break. To avoid that, there's ARP bolts that have a wave lock on them. And what that is a little wavy area around rather than knurling. And what that does, it locks itself in place just by the high and low ridges of the waves. Now, of course, when we go to a through bolt like this, these can be changed at any time, and there's all kinds of alloys on these, and the alloys are stamped on the ends. This one here says it's an Eagle 8740 ARP. That means ARP made the rod bolt, and it's 8740 steel. These usually have about 190,000 psi tensile strength. Stock bolts or lesser performance bolts have about 170,000 psi. When you get up into the Super Pro stuff, they have a 220 or 230,000 psi of tensile strength. That's a lot of strength. Now, anytime you change a rod bolt, you need to resize the rod. So when you take a stud and a nut like this, and you undo the nut and you push the stud back out, and then you push new studs back in, what that does is it relocates it, and it also puts the rod cap in a different position. That means the bearing is going to be in a slightly different position. So anytime you do that, you need to put the new bolts in, put the rods on a resizing machine, and resize them for correct roundness again. Otherwise, you're going to probably have bearing failure. You've got a good chance of that. Of course, when you do through bolts, these don't require any machining or anything on the rod. You can just pop these out, pop new ones in, and that's why most race motors use through bolts. They don't have to go through all that kind of stuff. Make sure when you're buying rod bolts, you buy a good brand. We use a lot of ARP stuff. This is ARP. There's other brands too that make some good bolts, but we're kind of ARP fanatics around here, and you can't go wrong with this type of stuff. Now, for you Ford fans out there, for the small block Fords, the weak link in a Ford motor, like a 289 or a 302, was the connecting rods, because they had little teeny 5/16 rod bolts, including the 5.0 motors. And the Chevys, though, they used a 3/8 rod bolt. Now, the early Chevys, what they call a small journal motor, early 327s and 283s, they used a rod bolt that was 11/32, where you have 5/16, 11/32, and 3/8. So 11/32 is right in the middle. Well, there's a little trick you can do with Ford motors is on a typical Ford rod, you can punch out the connecting rod and put a small journal Chevy rod bolt in it, the 11/32, and that makes the rod bolt stronger, which inherently makes the entire rod stronger. Now, there's always a saying, less is more. Some guys will go ahead and punch the rod out and put 3/8 rod bolts in there, and they think, wow, 3/8 rod bolt's better. Hello? You only have so much space on the rod right here. If we go drilling this hole out any larger, you're not going to have any meat left over here to make the rod hold the bolt in place. So you don't really want to do that. It's not a very good thing. So you want to stay with 11/32 size. Now, this rod right here I'm showing you is also a Ford rod. This is a Ford stroker rod. It's a SCAT 4340 I-beam, and actually has the length on it. It's 5.400, so it's a longer rod than a typical factory Ford small block rod. These have through bolts. Now, I said it earlier, you can do little additions to rods, or little things like polish the beams, remove the stress risers, put good bolts in them, do things like that if you're on a budget. For a few bucks more, though, you can buy a 4340 steel rod like this. Yes, it's got a wide parting line, but it's already been profiled and shot peened and everything, so it's been stress relieved. Even though the beams aren't polished, because it's 4340 steel, you really don't need to do that to these. You can take them out of the box and run them. Just check the sizes and install them. But these are upgraded with the through bolts. So for a few dollars more, you get so many more features. Unless you're really on a squeaky tight budget, go ahead and spend a couple extra bucks. These really aren't that expensive for all the features you get, and this rod won't fail you. I just want to show you a couple of things about connecting rods also. One thing is, when you're taking a connecting rod apart, you got to pull the cap off. Don't stick it in a vise. Don't take the bolts out, stick it in a vise, and hammer on it. All you're going to do is distort it. And these things, believe it or not, it doesn't take much to distort a connecting rod, and then you end up getting bearing failure. Make sure you use the proper tools. If you don't have one, go rent one or go to a machine shop and let them do it for you real quick, and you'll be much better off. This is a rod cap separator, though, and basically one of these is a proper way to do it. So you pull the bolt back just a smidge here, just put a little space in there. I'm going to put this on here and just pull it up, and it pulls the cap off. But I want to show you something. Now, rods are directional, and what I mean by that is if you look at this, the bolt is not centered. You can clearly see that there's more space over here than there is over here. That means the connecting rod needs to go a given way on the crankshaft. Well, if we look real close, we can see there's a chamfer right here, and on the other side there is not. It's a very small chamfer. Well, this large chamfer goes against the outer side of the crank. We talked about that in crankshafts where it's got the radius. Well, this is the area that's relieved there to clear that radius. So connecting rods aren't centered. You can't just put them on either way. And you got to be sure the cap's going the right way too. And I've seen engines come in with wobbles and stuff, and they're like, anyway, I can't figure out what's wrong with my motor. Well, on stock rods, this chamfer is not as obvious. And you can put a rod cap on backwards and wonder why the thing doesn't run right or has wobbles or you eat a bearing up. That's because the cap's on backwards. You've got to be careful of that. Now, if we look inside the connecting rod, when a connecting rod is sized, they do it for a reason, because they put, not only to make it a correct size, but they also put a cross hatching inside here. If you look real close, you can see little fine scratches in there. And what that does, that's from the honing marks of the sizing machine. And also, rod bearings have tangs on them. There's a little tang. If we look inside, most people know this, that there's a little tang in there, and that's what the bearing rides in. And some people think that that's to help hold the bearing in place. It really is, but these days, there's a lot of motors out there, brand new motors in newer cars that don't even have tangs on the bearings. What helps hold the bearing in place is this cross hatching back here. And that's the frictional value between that cross hatching and the back of the bearing and what we call bearing crush. And we'll talk about that more when we get into bearings, but the bearing crush is what forces this bearing into the rod cap and helps hold it in place. While we happen to have these rod bolts out, just wanted to show you. This is a big block Chevy rod, and obviously it's a larger rod, a longer rod. We were talking about rod bolts. Well, here's a through bolt right here. On this one is a 3/8, which is a typical small block bolt, and look at this monstrous 7/16 bolt. Obviously a larger rod, I mean, they're stronger. This connecting rod here is made for 750, 800 horsepower, sometimes more. So obviously the connecting rod bolts are much larger, which means they're much stronger. They'll take a lot more stress. Now, other factors in connecting rods are rod lengths. Now, we can look at these two different types of rods right here. They look identical. They're both H-beam 4340 rods, but there's a drastic difference in length in these things. The reason that is anytime you want to increase stroke, or you're going to make a stroker motor, you want to increase the rod length also. That takes away what they call the side loading of the piston, which has everything to do with ring seal. And also has to do with load on the side of the piston. That's why they call it side loading. Now imagine this. Here's the piston. It's going up and down the block, okay, inside the cylinder. It's going up and down. And the crank is turning this around as it's going. As we increase stroke, this starts swinging farther and farther out to the sides. Well, it's so short, it's really starting to swing. Well, what it wants to do, instead of pushing the piston up the bore, it wants to push it out the side. It puts more pressure on the outside of that. Well, what that does is it pushes the piston to the side of the cylinder, and it leaves this side over here wide open for the ring to really take up a lot of that space. Pistons aren't that tight in the bores, especially on a race motor, and you can actually get quite a bit of ring exposed over here. It leaves it wide open, and it can't really make a good ring seal. Less ring seal is less cylinder pressure, and the whole key to horsepower is cylinder pressure. So anytime you increase stroke, you want to increase the rod length, and what that does is it decreases the side load and helps the piston seal be better. So we use a longer rod like this. That way, as it's swinging around, the piston tends to want to be pushed up the cylinder rather than out the side. Now that works in theory, okay? Now there's a lot of people that'll argue with me on this, and that's fine. Everybody's got their own opinion. But dyno tests have shown, and these are some pretty high-end guys that are doing these dyno tests, that rod length doesn't have a whole lot to do with horsepower. There were several dyno tests done by a couple of companies out there that did nothing but make identical blueprinted motors. I mean, they were identical in every single way, shape, and form, dynoed on the same day. So there's no air pressure differences, atmospheric conditions, anything like that. And they did nothing different in the motors except have different rod lengths for the different stroke. So they all had the same stroke, but they all had different rod lengths. This was just to prove or disprove the theory of side loading and making horsepower. What the final results were was there wasn't a 1 horsepower difference between the smallest rod and the longest rod. That's the reality of it. Now, theory works. There's a lot of people out there, a lot of nerdy guys out there that do a lot of math, and they like to figure this out and figure that out. That's all fine and dandy. But a lot of times, theory and reality are completely two separate things. We talked about that earlier with cross-drilling a crankshaft. In theory, it adds more oil. In reality, because of kinetic energy and centrifugal force, it actually sucked the oil out of the rod bearings and starved the rods. So you're sitting there doing it on paper, it goes, yeah, that'll work. Put it out on a racetrack and you go, God, how come we're spinning rod bearings? We can't do that anymore. Theory doesn't always work in reality. Same thing with different like connecting rods. Now, I build a lot of stroker motors, and I still adhere to the old school days of long rods. If there's no horsepower difference anyway, then why not go ahead and run a longer rod in the first place? So whether it's true or not true, at my shop, I choose to run the long rods. Now, here's a hard thing that you run into sometimes. You're limited in what the length of the rod that you can run by the deck height of the engine. Now, this is just a typical small block Ford, okay? On these, we make up to a 347 cubic inch stroker on the little 289 blocks like this and 302s. The problem is you can only go to a given rod length. The longest rod we run in these things is a 5.4 inch, so it's 5.400 inch in length. A stock rod is 5.090 inch, so it's just 90 thousandths longer than 5 inches. So we increase it by quite a bit by going to the extra, going to a 5.400 rod. Now, in theory, we'd like to run a longer rod yet, but we're limited in the deck height. And what the deck height is the distance between basically the cylinder length. From the crankshaft to the top of the deck right here, the deck surface, that's the deck height. Now, aftermarket race blocks, we can run giant stroker cranks, and the way we get away with that is they got taller deck heights. Of course, they're designed internally too to accept a larger crank. They move water jackets out of the way and shorten inside the cylinder bores where they drop down inside the rotating area. They shorten that. There's a lot of things that they do to be able to fit a large crank in there. But also the trick is to make a tall deck block, and that raises this area up here. And that's why you have to have special manifolds and stuff like that to fit these tall deck blocks. The advantage of that is we can run a super long rod, and that helps with the rod angle on that and help with less side loading. Whether it actually works or not, the dyno tests have really shown that there's not a whole lot to it, especially in low horsepower motors. If you're talking a big wild 700 cubic inch like a Pro Stock style motor, there's probably a lot more to do with it on that end. On a low end, a 350 or 400 horsepower motor, it's really not that big of a deal. Although when we do talk like small block Chevys, I tend to run the 6-inch rods over the 5.7 rods. I like those. When we do 347 strokers, I prefer to use the 5400 rod as opposed to the 509 rod. So there's a lot of things that we like to do, whether it works in theory or not. I just tend to stay with the old school stuff and go ahead and go with a longer rod. One of the last aspects of connecting rods is cam clearance. Now, we talk a lot about crankshafts and strokers and stuff like that. Well, anytime you increase stroke, you also increase the crankshaft throwing the connecting rod up closer to the camshaft. I mean, the cam stays at a constant height. As the crank comes around, you increase stroke, it comes up closer yet. That also puts the connecting rod closer to the cam. So on cheap stroker motors out there, you'll see guys that will actually grind off the head of the rod bolt up on top, because as the rod is going around, the camshaft is in the center of the block. Well, as the stroke comes up and around, it puts this rod bolt right here on the inside rod bolt very close to the cam as it comes around. Well, when you increase stroke so much, it'll actually smack it, especially on 383 Chevy strokers. It's very common for that. Fords don't have too much of that problem. Reason being is the distance, come over here and look at this, the distance between the center line of the crankshaft and the center line of the camshaft is a greater distance in some instances, or the stroke is so short that it's really not that big of a problem. But Chevys, the way we get away with that is some aftermarket blocks have what they call raised decks, tall deck, and they also have a raised camshaft height. And what that'll do is get the camshaft up and out of the way of the crankshaft. Now, other ways we get away with that is running a small base circle camshaft, or like I say, the cheap strokers out there, what they'll do is they'll grind off that connecting rod bolt. Reason I'm telling you that? Don't do that. That's just weakening the rod. Even if you had stock rods and it's just a cheapy little stroker, you're still weakening the rod. If you went ahead and fixed the rods and polished them and sized them and put good ARP bolts in there, and then you grind the face off the rod up here, you're really asking for it, because now you just really weaken that connecting rod bolt in the head of it, and that's the only thing on this end holding the cap together. Don't do that. If you look at aftermarket rods, a lot of times they're profiled where they're shouldered. And if we look at this, you can see the distance of how the bolts stick up higher. See how high it is? And back here, you can't really see it. Up here, it sticks up. So when you buy aftermarket rods, a lot of times they're profiled to clear the camshaft. And that's how you can get away with more stroke and larger connecting rods, longer rods and everything, with the shoulders cut like that. Even on I-beam rods, they'll do that too. What they've done with these guys right here is because it's a through bolt coming up through, there is no bolt head up here. So they can get away with a shorter distance right here, and a lot of times these will clear strokers. So what have we learned with all this? On connecting rods, there's cast rods. Would I use a cast rod in anything for performance? No way. I don't use even cast rods in stock motors. Anytime I'm doing a build for somebody and it's got cast connecting rods in it, and the same engine was available with forged rods, I automatically try and get them a set of forged rods for it. Even if they're just old cores that I'm just resizing, I usually take the cast iron rods and chuck them. For a bone stock motor and you want to keep it original, these are fine. But for anything else, throw them out. Performance, for mild performance and medium performance, I-beams, whether they're 5140 steel or 4340 steel, you can't go wrong with a good I-beam. Up to 500 horsepower, this is awesome. Or a stock motor, or even nitrous, or even blown up to 500 horsepower, these things work great. That would be a good choice. If you're going blown, nitrous, or anything like that, and you're above 500 horsepower, then obviously a 4340 H-beam rod like this, that's the way to go. So don't cheap out on the rods. Like I say, it'll come back and nip you in the butt, and it's just not a good thing. You didn't put all that money in a motor to save a little bit of money somewhere to have it come back and destroy everything else in the rest of the motor. Now, there's one last rod I want to show you, and there's some special engines that actually have curved cylinders, and they use a connecting rod that looks like this for going up the curved cylinders. I'm just kidding you. This is what happens when you hydraulic a motor. There's no such thing as a motor with curved cylinders. When you hydraulic a motor, what that means is you blew a head gasket, or you cracked a head, or you cracked a cylinder, and the cylinder filled with water. Now, mind you, inside of an internal combustion engine, you're compressing air. Air compresses. Water doesn't. So water becomes a solid. So what happens is when the cylinder fills up with water, you got 7 cylinders turning that crankshaft around. This one's not turning anymore because obviously it couldn't light the flame inside with the water in there. But it comes up, has no place to go, so the rest of the cylinders actually bend this rod and torque it around like that. So when you see a bent rod like that, it's usually from a condition what we call a hydraulic engine.